Hey, welcome to the Explainer. In chemistry, it's all about having the right tool for the right job. And today, we're going to crack open that toolkit and pull out a really precise instrument for building molecules, the Gattermann reaction.
So picture this. You're a chemist, right? And you have to perform like molecular surgery. You've got this complex molecule, maybe a benzene ring, and your job is to stick one specific atom onto it without, wrecking the whole thing. It's a huge challenge chemists face pretty much every day.
So to pull off that kind of precision, you need a very specialized tool. And today, we're going to zero in on one of the most reliable reactions out there for tweaking those super stable aromatic rings. All right, let's get into the recipe itself, the Gattermann reaction. Think of it as a super precise two-step process for adding a halogen, we're talking chlorine or bromine, right onto a benzene ring. So, at its heart, the Gattermann reaction has one main gig. It cleanly and efficiently swaps out a really reactive group, this thing called a diazonium group, for a halogen atom. It's this beautiful, elegant substitution that basically gives chemists a handle to grab onto for building even more complex stuff later on. Yeah, it's a carefully staged two-act play, you could say. First up, you've got to create this all-important intermediate, the benzene diazonium salt. How do you do that? Well, you treat aniline with some specific reagents at a really chilly temperature. We're talking between 0 and 5 degrees Celsius. And that cold temp is absolutely key, because that salt is super unstable. Then, for Act 2, you bring in the Gattermann reagents. That's just copper powder and some acid, and that finishes the job. And here's the whole thing in a nutshell. On the left, you've got our star player, the diazonium salt. It gets mixed with the copper catalyst and the acid, and on the right, boom, you get your prize, the final product, the arrow halide. And see that little up arrow next to the end too? That's just telling you that the old diazonium group literally just bubbles away as harmless nitrogen gas. Pretty neat, right? Okay, so here's where it gets really interesting. The Gattermann reaction has this super close chemical cousin, the Sandmeyer reaction. They do kind of the same job, and because of that, oh man, they get mixed up on exams all the time. So let's do a little tail of the tape here, put them head to head. The big, fundamental difference between them, it all boils down to one simple thing. What kind of copper catalyst you're using. Okay, let's break this table down. For the Sandmeyer reaction, you use a pre-made copper salt. But for Gattermann, you're just throwing in some simple copper powder with an acid, and the catalyst gets made right there in the pot. But here's the real kicker, the most important difference. Look at the products. See that? They can both make chloro and bromobenzenes, no problem. But only Sandmeyer can stick on a cyanide group. That is the key distinction you got to remember. So if you're studying for a test, here's this simple memory trick to keep them straight. Just burn this into your brain. Gattermann uses copper powder. Sandmeyer uses copper salts. That's it. That one little word difference is everything. All right, so beyond just being a tricky exam question, why should we even care about this reaction? I mean, where does it actually show up in the real world outside of a lab? Well, it turns out the stuff you make with this reaction, halobenzenes, are absolute workhorses in industry. They're the critical starting point for creating all sorts of things, like the vibrant dyes in your clothes, the really complex molecules in life-saving pharmaceuticals, and even the building blocks for some super advanced polymers. Okay, let's bring it all home. What are the absolute must-know final takeaways from all this? If you're reviewing this for a class, listen up. Here are the 4 things you have to lock in. Number 1, that super cold temperature for the first step, totally non-negotiable. 2, your products are limited. You're only making chloro or bromobenzenes here. 3, and I'm going to say it again, no cyanide. That's Sandmeyer's job, not Gattermann's. And finally, number 4, if you can draw out how to get from aniline to chlorobenzene, you've basically nailed the core concept. When you step back and look at it, the Gattermann reaction is just a perfect example of a chemical tool that does one specific job, and it does that job incredibly well. I think our source material puts it perfectly, calling it a simple, neat, and high-yielding reaction for a specific, important job. Can't say it better than that. And that really leaves us with one final thought to chew on. If a simple common metal like copper can be the key that unlocks such a powerful chemical reaction, what other secrets are just waiting for us to find in the rest of the periodic table?